Hello everyone, my name is Lukasz Luba. I used to work for ARM Power team. Currently I work for Samsung R&D Institute in Poland. I'm going to present you some idea regarding the allocation of the power in Linux kernel scheduler. This is a new approach. I will give you some background. I used to work for ARM on intelligent power allocation and integration with EAS. And this could be considered as a second approach, but from different angle. So our agenda for today is to give you some background and some problem definitions and discuss existing solutions and then show you some proposal, the SchedPower, show you some results, and we can discuss also some future work maybe. So the background is, Professor Luka yesterday said, there is some issue with power management and thermal throttling. We have a few subsystems in the kernel, like the thermal framework and CPU framework. And the SoC platform has also, it's possible to have also some firmware to control the power management or thermal management. I assume that we have a full control over the CPU frequency here, and we have also control over the voltage. You will see some equation in the next slides. So no firmware is involved in the process, and we have full control over the SoC, and we can tune for our needs the power allocation. Oh, sorry, equation is gone. I did it in a Windows PowerPoint, and now I have to. Okay, I will discuss it. Okay, we have a power estimation, which is a total power considered as dynamic power and static power. And the dynamic power is actually heavily dependent of the voltage squared. When you increase the voltage, you actually increase the total power. That's why we have the OPPs on the curve. And the curve looks like this. It's exponential curve. Well, we live in the discrete world, so we have OPPs as points on that curve. Yesterday there was a talk when Douglas claimed that we can remove some OPPs from the bottom because they all share the same voltage. That's true. We can remove them, and we will probably nothing lose because we are also changing the frequency and the CPU load, so it could be considered as injecting idle, which I'm going to also discuss today. Here are some real examples how it looks like. It's a power versus performance plot. You have power here, you have performance here. It's a big cluster of the Exynos SoC. And here are the OPPs. And here's a new idea. Here's a straight line. It's called idle line. All the OPPs have this idle line. The idle line corresponds to idle injection. So for instance, when you inject 50% of idle, you will actually have like 50% of the performance of that OPP, but you pay at this cost, the corresponding cost. While when you apply proper algorithm for DVFS, and when you realize that you can decrease the frequency and also decrease the voltage, you can probably pick that OPP, and you don't have to pay that cost. Here is another example, another SoC. It's Samsung Exynos 64-bit ARM, a big cluster. Also a lot of OPPs, every 100 megahertz. It's exponential curve. Yes?
The idle lines that you're drawing here, these are actually the only real lines of the model, right? Like the points in between the OPPs, they don't really exist.
Well, we have a lot of OPPs
He
in
just
Samsung.
hasn't drawn them.
Yeah, that line is a linear approximation only to show you
Yeah,
that
but
the
that's the
curve.
thing. So if you have, so on say you have capacity on the x-axis, right, and power on the y-axis, and if you have, I don't know, an OPP that gives you 500 of capacity and you run it fast, it has 400 utilization, you will be running, your percentage of busy time is 4 out of 5.
Yes.
And so you will take that percentage of the power consumed at the OPP, and that will be your average power, so the energy you consume.
Yeah.
Right, so that's basically...
Yeah, you are actually traveling through this line.
Yes, exactly.
Yes.
So the line in between the OPP, you will never actually...
Is the ideal world?
that
Yes,
power.
that's the pre-calculated dynamic power. It's also in your energy model, can be because you are calculating the voltage squared times frequency.
Right.
So this is so that's the OPP ideal world. But actually,
Okay.
we are on that line.
Yeah, right. So we
It was implemented like that in IPA. Now it's simplified in energy model also.
Well, what we have are discrete points, right? So we never estimate power in between two OPPs like this.
Yeah.
We always look at the line that you're drawing here.
Yeah.
That's always the power we look at.
That's only to have a view that it's exponential.
Right. Okay.
If you just plot
It's
the
visual
dots,
thing.
yeah. Okay, we have another SOC. I don't know if we can talk about it. Let's skip it. Here's some background. What's the energy cost of computation? For instance, we have a time. This is a time. We have time 0 to compute something with some power related to that computation. So we just picked some OPP and we pay actually this energy, this box. And we cannot just assume that when we apply the real DVFS, so we decrease the voltage and we decrease the frequency, we will pay the same amount of energy. It's not true. It's actually like that, because we can shrink the voltage to minimize the power dissipation also. And thanks to that, we can have some relation between power, frequency, and CPU cycles. And shortly speaking, when we need more cycles, we need more power, or more power, more cycles. But we have to pay for this. Okay, so current SoCs must run under some thermal constraints. Some of them can easily consume something around 20 watts, even more. On my power supply, sometimes it drains 7 amps, while there's 4 volts. While you will see on the plots, normally the power dissipation from a thin smartphone is something around 3 watts, 2.5, it depends on the PCB and some other manufacturing processes. So it's not possible to utilize the highest frequency, as we discussed yesterday. Sometimes it's not even possible to utilize this frequency for a single CPU, even if you have 8. So what's the current situation? Simple power reduction, it is not optimal. The governors like stepwise or some other thermal governors, they basically react based on the temperature. And there is some more intelligent solution. It's called intelligent power allocation. It's mainline in thermal framework. And according to some benchmarks, it's probably the most tuned solution. It also reacts on the temperature and tries to estimate what's the power budget based on that. And as I said, the power is managed in the thermal subsystem. It's a completely different world from the scheduler. There are some other locking issues, etc. And unfortunately, it's a guard, it has a last word and it's a master in the system, and we cannot influence it in real time from the scheduler, and it's not aware of future work. Currently we have the EAS mainline. It's connected also with CPU Freak framework. It's not connected with the thermal framework. Some effort has been made, as I mentioned earlier, to merge these two solutions, which perform really good. But there are some issues. We cannot just simply go to the thermal framework, do some stuff, and jump out. And for my first approach, I tried to attack the problem from this angle, and now I changed the angle, and I'm trying to move the algorithms closer to the scheduler with different locking and with different assumptions. And here's a short summary how we can compare these two solutions. So IPA, as I said, it reacts on temperature and tries to estimate what's the power budget and tries to split the power budget across the CPU, actually across the clusters which share the same voltage domain and the frequency domain. And that's why it's still missing to have a fine-grained tunable for each CPU, while the SchedPower would have that. And rebalancing power across the cluster is also difficult for IPA, but it's possible. We have something called a contribution or a weight, but it's unfortunately a static read from DT. And rebalancing dynamically the power across the clusters, it's not possible for IPA, but it should be possible for SchedPower, because you can change the weights. Yes?
Rebalancing power across clusters statically. Why it's statically balanced?
Because you just define in DT what would be the split between these two clusters. Like that one will have 80% of the power budget, and that one will have only 20. That's it. You run. So it's not possible to dynamically rescale this shell. And reacting on the next calculation demand, it's not also possible for IPA. IPA just have statistics from the past, and we cannot influence about the future tasks in run queues. While if you have some simple API call from the scheduler, you can just change that calculation. And keeping the SOC under control and under thermal envelope, it's possible for both. So it shouldn't be an issue. Rebalancing power inside the cluster, that's also difference between these two. Currently, you just cannot split the power inside the cluster which has the same voltage domain, while with injecting idle, if you have a per CPU variable to control the CPU, the core, and you can have also a kind of a weight or some balancing mechanism, you can just say that, okay, I will grant full power to only one core and the other will go 100% idle. Increased frequency above existing thermal limits. It's not also possible for IPA, but I will show you how it could be possible for a SchedPower. It could be possible when we have this idle injection. So let's say we have this limited power budget for this cluster, and it would be possible if we inject idle for the other cores to increase the frequency for one particular core. And we use the DVFS for cooling. It's called passive cooling. We assume that we have no fan in the phone. Yeah, we use idle injection. We are closely connected to the scheduler, like the CPU free governor, and we can modify the power model, so those dynamic power coefficients.
So you're modifying the dynamic power coefficient, or?
Yes, if it would be needed, if you see that you cannot converge, you still have. I will show you some plot.
So you are auto-adjusting this?
Yes, because well, the issue was in IPA also that you must have expertise to tune the IPA. It took me weeks to run on some platform because the PID controller which is inside, it requires some knowledge from the engineer. And also it varies from platform to platform. You can have a different PCB with different SoC plays. So it would be nice if we can have an algorithm which will.
Instead of trying to modify the dynamic power coefficient, we should better play with the PID, the coefficient of the PID.
Yes.
Because normally the dynamic coefficient reflects some hardware behavior, stock behavior, more than how you want to stabilize with the platform. That's my point.
Yeah, we can discuss. Yeah, you are right. Also, we can discuss it offline also. That's a proposal. Yeah, I'm free to extend or modify something. So, one of the issue, it's not possible to reweight CPUs or clusters and grant more power for some cluster directly from the scheduler, like Professor Luka yesterday said, with deadline scheduler. And it's not also possible to allow higher frequency than it's capped. Might be critical for some deadline tasks. That's also worth to discuss what he would say. Okay, so where we are. We have a thermal framework which has those governors. They react on the temperature and they have passive cooling using the DVFS. Sometimes they implement simple rules like stepwise, just limit the frequency and go down. And there is no mechanism to change that. There is also some other thing regarding the implementation of the thermal framework. It uses thermal zones and it uses cooling devices. I've done some modifications. I grabbed their header, put it into include directory, and I wrap around some structures to have more control over those structures. And some other issue is that the code is not ready to be called from the scheduler. So let's move some good algorithms closer to the scheduler and create one file which will implement this governor. How the intelligent power allocation works. Unfortunately, it's a master in the system, so it has the last word. It just caps the frequency and notifies about that to the CPU framework, and it runs periodically. When there is a low temperature, it runs every 1 second. Of course, you can tune those too, but normally no one tunes it. And when the temperature crosses some threshold, it starts polling every 100 milliseconds. And it tries to estimate what's the power budget, and it uses the information from the past to predict what we do in the future regarding the CPU load. It's not aware about the tasks. That's why when I was trying to integrate EAS with IPA, it was hard to connect this also information. And the main algorithm is the PID controller. When you reverse engineer some thermal demons or power demons from some vendors, actually there is no magic. Well, they all use the PID, most of them they use PID, but it's closed in some magic daemon. It has some stubs from the kernel. Well, the IPA performs really good in the kernel. Why not use it as an open solution for everyone? But we have to modify some stuff. It updates the CPU freak subsystem, as I said, and it sends a notification. Here is the maximum possible frequency for you. That's it, unfortunately. And it has those static weights. So it's statically, when you run some experiments, you just rebalance and that's it. And you write it in DT. Here is some comparison between the power allocation and the stepwise, which I grabbed from the paper that I was also working on in ARM. What's the issue? This is a temperature, and this is a probability. So the main goal for IPA is to maximize performance in the thermal envelope and minimize the temperature deviation and use power budget smarter. The idea behind that is when we are jumping around the frequencies, we are choosing some OPPs, which is the maximum possible for the CPU. We are actually seeing the feedback in the temperature sensor. So when you are more closer to the destination temperature, actually it means that you are picking the right OPP. While in this case, probably the OPP wasn't correct, but you have to suffer for some, well, it's not some, it's a dozen of milliseconds to react and then increase the frequency again. So the control algorithm from the PID is quite good, as you can see. You can also check more information here in this PDF with some theoretical information and also some experiments. So what's the idea? Create something like that. Scheduler-driven power allocation. Let's create a new file in the kernel sched. I called it power.c. And allows the scheduler to change the calculated power budget across different clusters and different CPUs. Well, firmware does something. We see that sometimes it's not optimal. Some daemons tries to do the same. Well, they implement some, I don't know, microkernel ideas in this. Well, allowing scheduler to increase the CPU frequency above the limits and recalculating the power budget or injecting idle to the CPUs should be possible, easy, and easy to implement. And we can reuse as much as possible from the existing thermal data structures, the DT definitions, and I have also reused the idle injection framework. Yesterday we had a long talk with Vincent regarding that. It performs really good, but I had to move this header file to the include directory because it's not there. And yeah, to be compatible with many devices, so to create a solution for everyone. Here is a view of the SoC, and this picture shows the situation when the system is capped by the thermal governor, and those boxes, they represent the CPUs, and this one there are the clusters. And we can have this situation. So we can just rebalance the power across the clusters and grant more power dynamically to these two clusters. Should be possible. And also, we can grant power to a single CPU. As you can see here, we just grab the power from this tree, we inject the idle for them. Well, we are traveling through this idle injection line. There is some cost, but I will discuss it later. In extreme case scenario, we can grant full power to one single CPU. Should be also possible. Maybe to meet some deadline critical tasks. This is the situation when the system is balanced, the thermal capped the system. We have a system which is almost overloaded, and all CPUs are running 100% load. And this is the performance, this is the power. We picked some OPP, and this is the vector that we have to consider as a cost in the power. A total power is limited by the thermal. And what we have here, this is solution which injects idle to these 3 CPUs and grants more power to this one. So these 3 OPPs, these 3 CPUs which were stick to this OPP will actually, after injecting idle, will just go down here. Well, there is, as you can see, some extra cost related to this vector, while normally you would pay for this performance a little bit less, not a little bit, 3 times less sometimes, but you were able to grab the power and increase the frequency of the whole cluster and grant.
All the 4 CPUs in that cluster are powered by 4 separate power rails.
Yes, that's most, well, it's most popular example. While the SoCs, some they have the DVFS per core, but it's to implement DVFS per core, like in the silicon, you have to put the switches there, the inductors, which is more expensive. It consumes more silicon, but does almost nothing for the computation. While if you have the outside PMIC, you have usually 2 or 3 buck converters to power the clusters, and that's why the clusters rules the voltage and the frequency of the whole SoCs, CPU cores in there, in the SoC. So this is a proposal for a solution for those SoCs. And here is a corner case. The edge case scenario is when you inject idle almost 100% for the other 3, you actually don't pay a lot for that. Why? The leakage is even not squared, it's exponential. I will show you, the last slide in this presentation has the static power equation. So
This is all dynamic.
the model assumes that the dynamic power plays the role, like in energy model. We can experiment with that. Yes, the leakage, actually the leakage will be, normally it's 50%, static versus dynamic, 50-50. And also the leakage rises exponentially, and when you increase 20 degrees your temperature, you have 2 times more leakage. So from 40 to 60, from 60 to 80. That's also exponential curve. You can see it also in DD-RAMs on the datasheets. They provide you information called IDD5, which is the leakage when you are in self-refresh mode. So almost nothing. You just do some 1% just to refresh. But they do some experiments with the temperature. And what's the exponential curve of that current? So how is it connected with the scheduler and with the whole kernel ecosystem? We have the SchedPower here. We have some APIs connected with the scheduler, like for the request of higher capacity, or the API for rebalancing the weights. And we have also some thermal connections, just to create the model when we boot. So the thermal model takes the DT definitions and it reuses the thermal framework data structures. And we are connected also with the CPU freq. We set the maximum possible frequency also from here. Could be possible to replace the SchedUtil here. So not only announce what's the maximum possible, but immediately change it if there was a direct request from the scheduler. But for now, just announce that this is the maximum possible power, the maximum possible frequency for that power. The idea here is similar to the idea in the SchedUtil. We have some per CPU, we have this API calls, and then there is this asynchronous dispatcher which will do the work.
So it's basically because ARM hardware sucks.
Well,
so you're basically changing the load to change the frequency, which is completely ridiculous.
Well, this is the implementation which is popular on the market because of the money. As I said, if you are going to buy a phone with DVFS per core, which consumes a lot of silicon with the inductor.
It is having to use I2C to talk to external crappy components to change DVFS.
Yes.
We don't want this asynchronous work there.
But
it needs to die.
Well, then you have to talk with some other guy using not maybe I2C but SPI or I don't know some other buses, and you will always have the issue with locking there, that you have to sleep and wait for the reaction.
Well, we just want to register right. The end.
Yeah, that's ideal world.
We can mitigate that with some kind of a shared memory with a power processor that will take care of the I2C and so on. The main problem that we have right now is that we have to schedule a task to wait for the frequency to be changed.
Mm-hmm.
What we really want is to give the command. And then even if the
You are
change
still
will
hiding
happen,
the frequency change in that case. It will not happen immediately when you
No,
turn on the board.
it's-
You don't
it's
know
never
when
happen.
it will happen.
it's
So,
never happen immediately.
Yeah, exactly.
So you're just hiding the problem. You're not really fixing
Yeah, but
it.
it's the same for Intel.
It's not like that either, because even if you requested a regulator to do something, it will not do it immediately.
No,
Exactly.
So
Yeah, the regulator.
That's about, I mean, there is a value also on knowing exactly when you achieve that performance report, because we can update the stats and better track the signal, so it's a trade-off.
Again,
Also,
interrupting.
things don't happen immediately. Even if you change the voltage, then the frequency will take some time to ramp up. So it's not like
Well, changing the frequency is only changing the PLL. Waiting for the PLL lock is maybe 10,000 cycles max, or 2,000 cycles, while waiting for the voltage regulator that I have measured is almost 5 milliseconds.
yeah.
So
So
that's the difference.
But you have to wait for the voltage if you change up the frequency.
right.
True. True. That's why, yeah, you can discuss with me the implementation details also offline, why I just assume that we always have this issue.
So in your design, you assume that CPU are the main thermal contributor in the system. How you take into account the GPU thermal dissipation, the charger, the video, and all the other piece of the system that dissipate what?
Yeah, that's a good question. Actually, I spent 2 or 3 weeks to design and implement that, and the answer for your question is on my slide, one of the last one, future work. So I've done this research not as main task. Okay, so some test results and some basic checks how it performs if I move the algorithms from the IPA and try to stabilize the system, run the system, check if it behave well. And I've been testing on Exynos SoC. It's 5433. It's ARM64. It has 4 little cores and 4 big cores. I ran some benchmark like sysbench, and here are some results to check if the whole machinery is working, like injecting idle and changing the frequencies, and what's the behavior of the scheduler in that case. And this test scenario has 8 threads, the 8 processes, sysbench processes, and some of them they are pinned statically to big CPUs, 4 of them, and 4 are pinned to little, and when the big task will finish the computation, there should be possible to migrate the little task here. One of the core is having an idle injection all the time. I will show you on the next plot also. So we are injecting like 30% of idle here, just to check if all the machinery is not locking the system or just the system is not going to overheat. Here are some plots regarding the SOC temperature. We have a big cluster temperature, we have a little cluster temperature, and the whole SOC temperature. This is the whole SOC temperature. So we can see that we are convergent to some temperature. We are not jumping around with the temperature, as you could see on the plot with the IPA, from the IPA documentation. Some other plots. Here is the power budget, and you can see here is the power in milliwatts, and it's something around maybe 3 watts in here. It also depends how long I have been running the test, of course, because when I come to the office early morning and the phone was cold, then you can have a more power budget. But actually it reflects quite good the power budget, and it's actually power budget split between the two, the big cluster and the little cluster. As you can see, when it rises the power to, it grants the power to the little cluster, it also shrinks the power for the big one. And the reflected OPP is in here. So the highest OPP is with a 0 here, and that's the plot regarding in which OPP we are now. So as you can see, from time to time we get the lowest OPP almost on the big core, but I will show you different slides when I tune the system a bit more. And here is some comparison with stepwise governor. Well, the average frequency is 50% higher. That's because when you recall the temperature variation when you use stepwise, it's not intelligent, so it's not optimal. You can do some better stuff. And here is some other example how the power budget is jumping around when the system is not tuned properly. But you need this expertise, how to tune the PID, the coefficients, etc.
So you were complaining that IPA is hard to tune, but your thing isn't much easier?
Currently, it's the same, but there are some ideas. There was also when I was in ARM. So,
I have a question.
Yes.
How do you decide where the power budget goes?
how do you?
How do you decide where your power budget should dynamically be adjusted? Which
Normally,
get the power budget?
in this implementation, it's same as IPA. So,
Well, IPA uses static weights. You said on the comparison slides that yours are adjusted dynamically. So how's that?
no,
done?
this one is the first experiment when I set the static weight.
Okay.
So I don't rebalance because, well, there will be some different needs from deadline. So I will just give you an API, and you can
But you
just.
can also change IPA to do it dynamically.
Yeah, you can just write
It's not a
use
fundamental thing.
Oh, change the IPA and the whole thermal framework to react.
You just have
with
it
this.
I mean, it's most likely that user space knows how
Yeah.
how power budget wants to
Yeah,
be
you more
split,
than
so
knows
it would
those.
be natural just to adjust the weights in IPA.
Yeah, but you know those thermal demons. They are vendor specific. They are closed source.
But you're suggesting that it should be set by a tuning interface. How's that different?
Well, the difference between the thermal D somewhere in the user space, which is closed, and the open solution in the kernel, or
But you say you don't have an algorithm in the kernel to do that split. You rely on somebody to do it for you.
well, you can just assume that it could perform like IPA, and just you have an interface to increase, for instance, power for one single CPU for the deadline tasks. That would be the easiest case scenario.
Yeah, for deadline, but what about for CFS and all the other classes? I don't understand how the dynamic
Well,
allocation of power works in your code.
For the CFS, yeah, that would be probably impossible. But for the deadline, it could be possible to change for fixed period, to change and inject idle and
You
to
mean
grant.
that we have an API in kernel space to tune those parameters and the scheduler use that API?
Yes.
Okay.
Yeah.
Maybe
Currently,
you
I
still have to present it or?
yeah, there will be some other
Okay,
slides.
so maybe there are other slides.
Okay.
So the IPA also doesn't provide you to the mechanism to inject idle. While in this case, you can also, yeah.
Adding the idle injection in the CPU cooling device. So that the goal, so you provide the power budget to the CPU cooling device and then you split that between frequency capping or idle injection.
No, that's possible. Yeah, so as you can see here, for instance, injecting 30% of idle for those CPUs will actually, this is the whole big picture, will migrate the tasks to the liter core, the cluster with liter cores, and yeah, that's also something new from the IPI perspective. And here is how the power budget can be more convergent to some stable point when you do some tunes. As you can see, the total power budget in here is something around 2.5 watts. Some test results when I have injected 30% idle for 3 CPUs, and one big core was able to run with the max OPP. So I was a bit surprised that the static power was probably lower than 30% in that case. Another example, run 100 thermal power envelope, which is 2.5, and experiment with different settings for the PID and avoid the oscillations. So as you can see, the SOC temperature was converged to some 80 degrees here during the test, and how the power budget split behaved. Almost with no variation. And the frequency for that SOC when the power budget was split, something around 1.8 gigahertz. But yeah, we are injecting 30% idle. So yeah, here's some details about the implementation. It lives in the power.c and has those locking and the per CPU variables which are callable from the scheduler, and has this asynchronous dispatcher.
Have any head-to-head slides of how this compares with IPA? On a general Android benchmark that you run across both, it generates a huge amount of CPU and GPU load, something like.
No, currently I don't have that one. But it's yeah, it should behave same. Yes, Javi?
The figures that you're showing for power are all calculated during using dynamic.
Sorry, I cannot hear you. There is some rumor in here.
The figures that you have for power, they are all calculated using the power models that you have. And that includes the power consumed for the idle injection.
Yes.
So you are assuming that the idle injection is behaving the way you...
Yes,
yeah,
the straight line.
Like that.
Yes.
Do you have actual measures that confirm that?
Well, you are somewhere in between this the idle line and the exponential curve, but closer to the idle injection line, because the voltage cannot be shrinked, so you are still fixed to this voltage, and the leakage is the same, but you are actually only injecting idle for some.
Yeah, that's what I'm trying to get to.
We didn't have experiments for IPA how it behaves with the idle injection back then, but Okay.
Question of the interface. But so in your approach, if I understand correctly, you would allocate power to a given CPU and say this one can take all the power and the other ones will have nothing. But then, so because you want something important to run on that CPU.
Yes.
But then what prevents the scheduler from taking that important task and putting it somewhere else?
Well, this is the implementation, the first step.
Right.
As Vincent, I think, mentioned, what about the CPU and GPU? So currently from the scheduler, it's hard to control the other guys. While in this case, for this implementation, I just implemented the model for the CPUs. But IPA also has the GPUs and other stuff. So when you move also the other guys in here, that's the difference. Well,
the question was, I think, how do you synchronize the power allocation with load balancing?
Right. Because it feels like something that should be expressed on a per task basis rather than per CPU.
I think that's the fundamental problem of trying to implement the power budget on the CPUs. If you start to sort of squeeze cores because you think they shouldn't use as much power, the scheduler is most likely just to move the task somewhere else. So it's a game where you just keep chasing the CPU that's currently got the task running, unless you coordinate the two. But I think the better solution is to turn it around and not do the capping per CPU. You need to do it per task, because then the scheduler can't do any tricks.
Well,
so what you really want to do is to figure out which task can I sacrifice at the moment and apply clamps to those, regardless of where they are. then you don't have to worry about all these things.
Well, what about the GPU or some DSP cores? The GPU, when you are overloaded and you don't have mechanisms like from IPA to grab the power budget from the GPU and DSP and say that, okay, I just...
You can still use IPA to govern the split between the CPU and the GPU. We're talking about how to split the budget inside the CPUs, because you have big and you have little CPUs, you have multiple clusters. How do you split the power budget in there?
It's not there,
IPA,
Morten.
as it works today, decides on a per CPU basis where the clamp should be applied, where reality is that the task might just move around to avoid those clamps that you apply.
Well, I would disagree, because IPA currently doesn't provide you this reweight for the GPU versus CPU power budget split. It's not there.
But it could.
It could. It's not there.
Oh, well, so that is not IPA, but I have a general comment, but I would rather see all the slides and then...
Yeah, I have 2 minutes, so let's shrink. Yeah, there are some other validations. Yeah, the future work. As I said, the power budget is currently only for the CPUs, while it would be possible also to reweight the GPUs or DSPs to sacrifice, for instance, the user interface and just give it more power to the CPUs which are running the deadline tasks. So that's the main goal, actually. Instead of tracking which task is using the GPU, just shrink a bit the GPU power budget or some other component and move it to the cluster which needs more power. And maybe some hints from the middleware, if there would be a need. And yeah, consider wider use cases. If Professor Luka would be interested, I can discuss with him some use case scenarios that I can test with them. These new cooling devices, it's worth to add in this implementation, and experiment with replacing the schedule totally. Yeah. And that's the equation for the static power. As you can see, the power rail, the voltage domain is exponentially related here. Sorry?
Normally your static leakage is increasing power of 3 of the temperature as well.
Yeah, I will rewrite this slide and I will send Yuri so you can check.
Yeah, time for question.
Last question? Yeah. Please.
Yeah. So you've tested this on a mobile SoC, and some of the idle injection that you've shown there is injecting like milliseconds of items. How does that play with workloads like the one Alessi presented yesterday, that you have to run 3 tasks consecutively in a 16 millisecond period?
Mm-hmm.
And if you idle inject on a CPU where that task was supposed to run, it's going to be delayed to the point of probably missing a frame.
Yes, yes.
So how do you...
Well, you can inject, it's not ideal solution. You can inject idle for the 3 CPUs and just grab the whole power for 1 CPU and just run on that one with the highest OPP possible. And yeah, maybe that will fit your need to run 3 consecutive tasks on that CPU.
Okay, so
delaying.
I think that example is no different. Either you're running at a lower power, either you have a lower budget because you've lowered the frequency, or you have a lower budget because you've injected idle. Either way, you miss the deadline because you have a low budget.
No, but the thing is,
You
you're
know,
running
it's
at a
identical.
lower
The
frequency.
problem's the same though. Just imagine it that you've moved to a low capacity.
Well,
yeah, but
if the
running at a
periods
lower...
are not the same, your
Yeah.
experience might vary. If your period
Your
of
interval of
idle
work
injections
over
is very long.
I agree if the idle injection period's too long.
Yeah.
But I
But
think on like
otherwise,
a
yeah.
16 millisecond period, which is the integral over, then I don't think that's true.
The average bandwidth is the same, I agree with that.
Yeah,
But it might come very lumpy.
Yeah, but
if
you've got a 16
period.
millisecond period. I suspect that works out to be the same.
And his goal is that, so, because you have 1 CPU with all of the compute capacity, the goal is to pack all the tasks on this CPU.
But the problem is to coordinate idle injection with scheduler.
Oh yeah, I agree.
That's
I agree.
definitely required.
So I guess what happens is that if you inject idle, then the scheduler sees that oh, the CPU is not available, because idle injection in fact is a real-time task, which you need to remember. So from the scheduler perspective, it looks like something is running on this core CPU, and it's occupying it entirely, so I can't schedule anything on it. So by and if you decide to move all the other things to the cores that have no idle injection on them, but I think that in general, it is the perspective that you can drive power allocation from the scheduler is kind of backwards, because the power will be allocated by something else, because you have different components to the system. It's like the GPU, the display, other things that may consume more power than CPU, let's be honest. Like there are accelerators, there are other things. So there will be something that will distribute power, and the scheduler will get some of it, but not all of it to the side. You know what I mean?
But there's 2 things here, right?
That's what you do with what you have left.
I think the way one put it made sense. You could have something like APA giving the scheduler a budget,
Or it could be hardware,
or
firmware,
hardware, whatever. But like
There is a budget for your
half of what he's
CPUs.
trying to do here is just how do you have the scheduler work within that budget, which is not the same problem as what you're saying.
No, it is not the same.
But that's the problem that might make sense.
Yeah, so generally speaking, it needs to be, you can't really use all the OPPs and stuff to figure out things. You will get some budget.
That's
From some
how you
things.
what piece are in how you spend that budget.
Yes.
Yeah, and then you have to figure out how to spend that budget, but that doesn't depend on the hardware configuration of your system.
Why not?
Because say something in user space decides that, oh, the GPU gets like 80% of the power budget,
But that's
and I will have 20%.
how's that different?
No, it is different because in this case, all this, if my
No,
understanding is
but
correct.
table 1 said, like, pretend you've done that arbitration up front, and you've given 20% power budget.
Yeah.
But that varies according to use case as well, it's never static.
I'm not saying it is.
You have just the 2 little
Yeah,
tests.
this is just working within the current budget. Like,
You have 1 volt
No,
investment,
so what
19 of cowbell.
what I'm trying to say is that it is follow the decisions are made based on the DT provided data.
And what I'm trying to reflect is that I think you're too statically taking what Lukasz discussed as the model. And I take some of the comments that Morten said and think about how you get the price and
No, so I understand that the scheduler has to decide how to distribute power within a given budget. But my point is that this budget depends on time, depends on.
It will change over
Yeah.
time. That's just a
Depends on
fact.
time, and then depends on.
So one of the proposals mentioned was to have that budget be an input rather than be owned.
Right. So that's my point, basically.
Okay. I think you're in agreement.
Yeah, we are in agreement. But I'm saying.
Okay, and with this we have to.
Thank you.
Thank you.